Welcome to the Explainer. Today, we are diving into something absolutely wild. We're demystifying how a tiny, honestly kind of insignificant 19th century botanical observation, literally just a guy peering through a primitive microscope at some plant dust, somehow unlocked the hidden, chaotic mechanical rules of our entire modern world. We're talking everything from the kinetic theory of gases all the way to how we model the stock market.
So, right off the bat, here's the mystery we need to solve. How exactly did a dancing speck of pollen prove that atoms exist? I mean, on the surface, plant biology and the kinetic foundations of physics seem like completely different worlds, right? But, as we're going to see, the random jitters of organic material suspended in water gave us the very first undeniable physical proof that our universe is made up of invisible, constantly moving molecules.
To really appreciate this leap, we got to step back and look at the massive timeline here. It all starts way back in 1827 with a British botanist named Robert Brown squinting through his microscope. Then, jump ahead decades later to 1905, where a young Albert Einstein actually uses Brown's observations to mathematically prove the existence of atoms. Fast forward again to 1986, and you've got computer scientists like Chris Langton using these exact same principles of random motion to build these incredibly complex digital simulations. It's a huge journey.
Okay, let's dive into this. Part 1. Busting a scientific myth.
Look, if you open almost any science textbook right now, or even some major scientific journals, you're probably going to read that Robert Brown looked through his microscope and saw whole pollen grains moving around in the water. Well, that is completely false. It's actually one of the most widely propagated mistakes in all of scientific literature. Brown was looking at the pollen of a plant called Clarkia pucella. Now, the pollen grains themselves are massive. We're talking about 100 micrometers in size. What Brown actually saw dancing around were the tiny 5-micrometer particles from inside the pollen grains.
And the absolutely crucial number here is 19. Why does 19 matter? Well, thanks to Einstein's famous 1905 equation on kinetic theory, we can calculate exactly how much a massive 100 micrometer pollen grain would actually move in room temperature water. The answer? Just 19 micrometers in an entire day. That pace is crazy slow. It's practically impossible to observe with the naked eye, and definitely impossible with the clunky optical microscope Brown was using back in the 1820s.
And you know what? Brown actually knew this. To prove this wasn't just some modern realization, we can look right at his own published paper from 1828. He explicitly wrote that the pollen grains were filled with particles very evidently in motion. He knew exactly what he was looking at. For a particle's motion to be visible to the eye in a matter of seconds, it has to be incredibly tiny, like 1 micrometer or less. Brown was seeing the microscopic inner contents of the pollen wildly dancing around, definitely not the giant pollen grains themselves.
Which brings us to part 2, the microscopic bumper cars.
This zigzag madness is the very essence of Brownian motion. Basically, it's the random, irregular movement of suspended microscopic particles in a fluid. But why does it happen? Well, it happens because of unequal collisions with the fast-moving molecules of the fluid itself. The path these suspended particles trace is completely irregular. It's totally unpredictable. It never stops, and it never ever settles. So the crucial point is understanding this dynamic. Picture a microscopic game of bumper cars. You have the dispersion medium, let's say the water. Those water molecules are invisible to us, but they are in constant, rapid, random motion because of their kinetic energy. Then you have the dispersed phase, the slightly larger, suspended particles, like those tiny pollen specks. The fast-moving water molecules act like super aggressive bumper cars, smashing into the suspended particle from all sides. But because the strikes are unequal, like maybe 3 molecules hit the left side while only 1 hits the right, the particle gets violently shoved in random zigzag directions.
All right, let's move to part 3, hot water and zigzags. Now, Brownian motion isn't just some static, unchanging rule. It actually changes based on a few physical variables. Like we just talked about, smaller particles move way faster because those molecular collisions have a much bigger impact on their tiny mass. Viscosity matters too, right? Particles are going to move much faster in a thin liquid like water compared to a thick, goopy liquid like honey. Density plays a role, because more dense fluids mean more molecules to collide with. And finally, temperature. Interestingly, this entire phenomenon cannot happen in solids. Why? Because the particles in a solid are rigidly locked in place. This is strictly a liquid and gas party.
And this brilliantly illustrates the physics at play. If you want a visual, think of that classic DIY demonstration with food coloring. If you drop coloring into a glass of cold water, it just kind of sinks and spreads out super lethargically. But if you drop it into hot water, the color violently and rapidly dissolves, mixing into the water almost instantly.
What you're really seeing in that hot water glass is Brownian motion in absolute overdrive. High temperature directly equals high kinetic energy. By heating the fluid, you're basically injecting pure energy into those invisible water molecules. They start racing around at much, much faster speeds, which means they bombard the food coloring particles with way greater force and frequency. The bumper cars are suddenly moving at top speed, causing that dispersed phase to frantically zigzag and mix into the medium.
Let's move to part 4 and see how this builds into math, code, and finance.
It is literally staggering how many modern fields rely on the math derived from Robert Brown's pollen dust. I mean, first, as Einstein showed, it was the definitive proof of atomic theory. No big deal, right? But it's also the reason why colloids, things like milk, stay stable. Brownian motion literally prevents the fat particles in milk from settling to the bottom due to gravity. But wait, it goes way beyond chemistry. This mathematical randomness is used heavily in probability theory, including the random walk hypothesis, which analysts use to model the highly volatile zigzagging prices of the modern stock market. It even bridges over into computer science and digital art. In P5.js coding, developers actually use the principles of Brownian motion to create generative art. A super famous example of this is Langton's ant, created by Chris Langton back in 1986. It's a digital simulation of a hypothetical ant taking random, probability-based steps on a grid. Now, at first, the ant's path looks like pure, unpredictable chaos, just a mess. But over time, based on very simple rules, that seeming chaos suddenly organizes into incredibly complex, orderly bridges and tunnels. It's like a giant puzzle coming together on its own.
Which brings us to our final section, Part 5, The Invisible Master of Chaos.
Think about this. A solitary botanist in the 1820s, just trying to look at some plant dust, accidentally pulled back the curtain on reality itself. That single observation unlocked the kinetic theory of gases. It explained how momentum transfers invisibly all around us, keeping particles afloat, driving the dispersion of chemicals, and dictating the chaotic mechanics that, quite literally, drive the entire universe.
So I want to leave you with a thought, one provoked by Langton's ant and the very nature of Brownian motion itself. When we look closely at the universe, it appears to be nothing but violent, random bumper cars, just pure, chaotic collisions. Yet, out of all that randomness, we get the stability of the liquids we drink, the gases we breathe, and the incredibly complex structures of life. So ask yourself, where exactly is the line between pure, random chaos and hidden order?